Okay, 3.38 is a Heisenberg uncertainty problem where we are dealing with time and energy-based uncertainty. It does appear sort of like a basic math problem initially because you're pretty much just being asked to validate that the uncertainty principle is actually true, given some constraint on what your uncertainty on time is supposed to be. But that being said, if you actually do solve this all the way through, the resulting answer that you get is sort of physically significant and has sort of consequences that you can sort of inference. And that does make it kind of an interesting problem to look at after we actually solve it. So let's start by solving it. Our goal for this problem is to prove the Heisenberg uncertainty principle, which is that uncertainty in time times uncertainty in energy has to be greater than or equal to h bar over 2. The constraint we are given is that we have to define delta t as tau over pi, where tau is defined as the time it takes for an arbitrary wave function to evolve from an original state, psi of x comma 0, into some new state, psi of x comma tau, where that state is orthogonal to the original state. We are told to test this using a wave function that composes itself of a linear combination of two orthonormal stationary states of some arbitrary potential. So we are given some initial wave function, which is, hang on, my drawing tablet is slightly, there we go. We are given some initial wave function, which is that psi of x comma 0 is equal to 1 over root 2 of some stationary state psi 1 of x plus some stationary state psi 2 of x, where psi 1 and psi 2 are part of an orthonormal set. Now, our goal is to find or to redefine tau so that we can figure out how to write tau in terms of the variables that you typically find in a wave function formula. So to do that, we can recognize that, okay, if psi of x comma 0 is this, and this is composed purely of stationary states, well, this implies that you can write this in terms of separable solutions, right? So that means that if you have a stationary state, the resulting time dependence from separable solutions is psi, whoops, it's a bit messy, psi of x comma t is equal to psi of x multiplied by phi of time. Since this is composed of two stationary states, you can rewrite this with time dependence as two separable solutions. This means that psi of x comma t is equal to 1 over root 2 psi 1 phi 1 plus psi 2 phi 2. And at this point, we know that at some time tau, that's going to be our time of interest. So let's rewrite this in terms of tau. And we can also rewrite this with explicit time dependence because we know what form the time-dependent solution to the stationary state is, right? This is equivalent to 1 over root 2 psi 1 times complex exponential e to the I e1 times tau divided by h bar plus psi 2 e to the I e2 times tau divided by x bar. And because at this point this term is now orthogonal to the initial term, this means that the inner product is going to be 0. So the inner product of psi x 0 with psi x tau, I don't know why I wrote this out of order, there we go, is going to equal 0. If we write this out as an integral expression, this implies that the integral from negative infinity to positive infinity of psi star x comma 0 multiplied by psi of x comma tau has to equal 0. Let's add that dx really quick as well. Okay, so let's combine this out. The two terms of 1 over root 2 become a 1/2 at the front, We have an integral from negative infinity to positive infinity. And then we have psi 1 star e to the negative I e1 tau over h bar plus psi 2 e to the I e2 tau over h bar, or negative I. And then this is being multiplied against psi 1 plus psi 2. If we then do distributive property, 1/2 integral negative infinity to positive infinity, psi 1 star times psi 1 e to the negative I e1 tau over h bar plus psi 1 star psi 2 e to the negative 1 or negative I e1 tau over h bar plus psi 2, and I forgot the star here, psi 2 star times psi 1 e to the negative I e2 tau over h bar plus psi 2 star psi 2 e to the negative I e2 tau over h bar. All this closed by dx. Now, the next thing we know is that psi 1 and psi 2, as told by this problem here, are orthonormal stationary states. That means that they are orthogonal and they are pre-normalized. If they are orthogonal, then any integral that involves, a double product of them, psi 1 star and psi 2, or psi 2 star and psi 1, respectively, or psi 2 and psi 1, or psi 1 and psi 2, etc., automatically cancel out to 0, so we can ignore those. Similarly, integrals of psi 1 star with itself and psi 2 star with itself, because they are normal, just go to 1. Which means that this integral resolves as 1/2 e to the negative I e1 tau over h bar plus e to the negative I e2 tau over h bar. And this is supposedly going to equal 0, because remember, at the very start, we said that this integral expression has to equal 0 due to orthonormality. Okay, now we actually have an equation that we can sort of try and get this to actually equal something in terms of tau so that we can rewrite it into the uncertainty principle. So immediately, I am dealing with a complex exponential. This seems like I should be converting it into a sinusoid. So if I look up my formula sheet, complex exponential to sinusoids, and I want to convert this into sines and cosines. Let's see. Yep, here we go. I have the following identities to work with. If I copy paste them into here, I know that sine of x and cosine of x can be redefined in terms of complex exponentials as follows, right? So if I'm dealing here with, let's write this in red, e to the negative ix plus e to the negative iy over 2 is equal to 0. This sort of implies that maybe I can split this into cosines and sines, right? So let's see. Complex exponentials. I know that e to the I omega, or not omega, I don't know why I'm doing omega, e to the ix is equal to cosine x plus I sine x. So if I have 1/2, this is going to be cosine negative e1 tau over h bar plus I sine negative e1 tau over h bar plus cosine negative e2 tau over h bar plus I sine negative e2 times tau over h bar. And this is supposedly equal to 0. Now let's do a little bit of simplification. So the 2 automatically just distributes out. So what I actually have is, let's see, cosine negative e1 tau over h bar plus cosine negative e2 tau over h bar plus I sine negative e1 times tau over h bar plus I sine negative e2 times tau over h bar, and this is equal to 0. Okay. Now at this point, I don't really like the fact that I have negatives inside my sinusoids. So I do want to recognize the fact that some of these are symmetric, right? So I think, is it cosine that's symmetric? Yeah, cosine is symmetric about the y-axis. So this is actually just equal to cosine e1 tau over h bar plus cosine e2 tau over h bar. And then I think sine is negative, right? So this is going to be minus I sine e1 tau over h bar minus I sine e2 tau over h bar. And this is going to be equal to 0. Okay, so at this point I have 2 cosines adding and 2 sines adding. Kind of stuck with no real way to sort of simplify this that much further. So inevitably I'm going to try and use trig identities to sort of massage this into something that I can further continue to cancel. In this case, because I have addition happening between sine and cosine, or cosine with cosine and sine with sine, I suppose, the thing I want to use is going to be sum and product formulas, which are these, right? So in that case, I have a cosine A plus cosine B. So this term in green is immediately going to come down. Number 1, right? This is going to be, let's see, 2 times cosine, let's make that a little bit neater, cosine of e1 tau over h bar plus e2 tau over h bar, all divided by 2. Let's make my parentheses a little bit bigger. And then cosine e1 tau over h bar minus e2 tau over h bar divided by 2. And then for this term in red, this is negative I times sine e1 times tau over h bar plus sine e2 times tau over h bar. So based on that, we're using sine A plus sine B, which is going to give us negative 2i of, let's see, sine A plus B half, so e1 tau over h bar plus e2 tau over h bar divided by 2 multiplied by cosine A minus B over 2, so e1 tau over h bar minus e2 tau over h bar divided by 2, like that. And then we can just combine these, right? So remember, we started with this, right? We started with the inner product expression, and we've made our way all the way down to this. So let's actually rewrite this so that we don't forget what exactly we're trying to solve in the first place. this is going to equal, I'm going to rewrite this in green and red, 2 times cosine of, that's 1/2 E1 plus E2 tau over h bar. Yeah, and then cosine 1/2 E1 minus E2 tau over h bar. And then we're subtracting 2i sine 1/2 E1 plus E2 tau over h bar cosine 1/2 E1 minus E2 tau over h bar. Okay, and at this point we can do some more distribution, right? Because there's a shared term here. We have a cosine term and we have a cosine term. Whereas on this side we have a cosine term and an imaginary sine term. So that implies that we can distribute out this cosine and the remainder inside is going to turn into a complex exponential. And this whole thing, remember, still equals 0. So that tells us that we're going to be able to make this neat little product thing that we can then sort of work off of from there. So this is going to equal cosine of, in fact, let's add the 2 cosine at the front as well. 2 cosine, or no, we can just get rid of it because there's a 2 at the front of both of these terms, right? There's a 2 here, there's a 2 here. So we can cancel that. We can say cosine of 1/2 E1 minus E2 tau over h bar, and then multiplied by cosine 1/2 E1 plus E2 tau over h bar minus I sine 1/2 E1 plus E2 tau over h bar is equal to 0. And now in the middle here we have a complex exponential identity, right? Because this, if we bring it all the way down, right, this is e to the ix, this is basically e to the negative ix, right? Because e to the negative ix equals cosine x minus I sine x, right? So this is an e to the negative ix term right here. And let's do this in a different color. This whole thing is just e to the negative ix. And because it's a complex exponential, or because it's an exponential in general of x, no matter what value x takes, this is never going to equal 0, right? So if this is never going to equal 0, and this expression as a whole equals 0, that implies that this term right here is the limiting term that has to go to 0 in order for this expression to be true. So we can get rid of the entire complex exponential, and we only have to work with this cosine now. So now we know that cosine of 1/2 times E1 minus E2 times tau over h bar is equal to 0. Now, for that to be true, the internal term has to be some half multiple of pi, right? It has to be pi half, 3 pi halves, 5 pi halves, etc., etc. So we know now that 1/2 E1 minus E2 times tau over h bar has to equal some multiple of pi half. So that's 2n minus 1 over 2 times pi, where n is, plus minus 1, plus minus 2, and so on and so forth. Okay, now we're almost there to solving for tau. There's a few restrictions that we have to keep into account. So the first thing that's really important, right, is that tau is time. Time cannot be negative, right? Time has to always be some positive value or 0. So in that case, that puts some restrictions on sort of what signs certain things can take. Because if you see here, E1 minus E2, this is less than 0, right? Because energy 1 is the base state energy or some lower state energy, and energy 2 is hypothetically some higher state energy. So if E2 is greater than E1, this term is going to give you a negative. Now, we have two ways to sort of resolve this. One is that we only stick with negative terms of n, right? N is now equal to -1, -2, -3, and so forth. Or we restrict n to positives and just arbitrarily slap an absolute value onto this. Either one sort of satisfies the condition we need, which is that the resulting tau term needs to be positive. So I'm just going to slap on absolute values because I like everything to be positive. I don't like my n's to be negative. So I'm going to say, okay, 1/2 magnitude E1 minus E2 times tau over h bar has to be equal to 2n minus 1 over 2 times pi, where n is equal to 1, 2, 3, and so forth. Some sort of positive integer. Now, if I take tau, right, the 2 here cancels for the 2 here. Tau is equal to h bar times 2n minus 1 times pi divided by the magnitude of E1 minus E2. So this means that our initial wave function psi of x comma 0 is going to evolve over time. And at time tau, it is going to become orthogonal to the original wave function, but then it's going to evolve more and it's going to become not orthogonal, and it will periodically become orthogonal over intervals of n, which means that we are told that t is the time it takes to evolve into a state orthogonal. So we're going to assume that it's the first time it becomes orthogonal. So we're going to say, okay, assume that n is equal to 1. This is the first period in time where my wave function evolves to become orthogonal to its x comma 0 state. So in that case, tau 1 is equal to h bar times pi divided by magnitude E1 minus E2. Okay, so at this point we have tau. Remember that we originally said that we want to enforce that the uncertainty in time is defined as tau divided by pi, which means that this equals h bar over magnitude E1 minus E2. And now we have 1/2 of our equation done, right? Because remember, the uncertainty principle is delta t, delta E greater than or equal to h bar over 2. We have delta t, we do not have delta E. So we're going to have to find the uncertainty in energy. Now, fortunately, this is a very simple thing, right? Because we are given the wave function at x comma 0 being equal to 1 over root 2 of stationary state psi 1 plus stationary state psi 2, where this has an energy E1 and this has an energy E2, right? So, if you just look at this, this is a very convenient wave function to have because that means that my wave function is perfectly split between the psi 1 stationary state and the psi 2 stationary state, which means that the probability of being in psi 1 is equal to the probability of being in psi 2, which is equal to exactly 1/2, right? If I take this term, right, the 1 over root 2, it's applied to both psi 1 and psi 2. Taking the magnitude squared gives me 1/2, which is the probability of being in psi 1 and also the probability of being in psi 2. This means that the probability of being in energy 1 is also equal to the probability of being in energy 2, which is exactly 1/2. So if we then apply standard probability problems, right, or standard probability formulas, right, the expectation value of the energy is going to be probability 1 times energy 1 plus probability 2 times energy 2. And similarly, for E squared, probability 1, energy 1 squared plus probability 2, energy 2 squared. Okay, in that case, the uncertainty in my energy is expectation E squared minus value of expectation E itself squared, like that, as we've defined so many times before. This is going to equal square root of, let's see, 1/2 E1 squared plus 1/2 2 squared minus 1/2 E1 plus 1/2 E2 squared. My canvas is running out of space. Properties, let's give it height of 10,000. There we go. Okay. This equals the square root half e1 squared plus half e2 squared minus, let's see, 1/4 e1 squared plus 1/4 e1 e2 plus 1/4 e2 squared. And if I cancel out the parentheses, right, all of these terms become negative. There we go. Okay. And at this point, right, this is starting to look a little bit like a quadratic formula. This is going to give me what? 1/4 e1 squared for these two terms, plus 1/4 e2 squared for these two terms, minus 1/4 e1 e2. Okay, there we go. We can just, you know, this is a quadratic equation. So this is just going to be square root half e1 minus half e2 squared. Is that correct? 4th e1, 4th e2 minus 1/4 e1 e2. Yeah. Okay, so that means that this equals half e1 minus half e2. But remember, once again, e2 is greater than e1. So we can't have a negative in our square root. We have to enforce it with a absolute value. Okay, and now this is our delta E. So finally, delta T, delta E is equal to delta T as being defined up above, h bar E1 minus E2, and then multiplied by 1/2 magnitude, magnitude E1 minus E2 divided by 2, like that, right? So in that case, this term cancels with that term. You have h bar over 2. This is greater than or equal to the minimum value of h bar over 2. And that is this problem. Okay, so we have one more thing to discuss, which is the physical implications of getting this answer. So we know that the uncertainty principle basically tells you sort of the limit to what you can know about a system. Normally it deals with delta x and delta p, which is sort of the combination of how accurately you can know the position and the momentum of a particle before sort of the wave function prevents you from looking more in depth, right? When we switch this to delta t and delta e, delta t is a little bit of sort of a mystery quantity because we're not used to measuring in terms of time. We're not used to using time as sort of a dependent variable, right? We're used to it just being on the x-axis and we measure something with respect to time. We're not used to actually measuring time. However, in this problem specifically, they defined delta t as tau over pi, where tau is the time it takes for a wave function to evolve into a state that's orthogonal to the original state at time equals 0. So what exactly is orthogonality? Right? Because when we think about orthogonality in terms of geometry, it represents sort of how perpendicular a thing is to another thing, in this case, vectors. When we deal with wave functions, right, what we found was that if something is taken an inner product of with itself, then it equals 1. Assuming that it's normalized, right? Whereas if something is orthogonal, psi1 and psi2, for example, we show that that is equal to 0. So orthogonality in geometry is a measure of how parallel two vectors are. In quantum mechanics, when you're dealing with wave functions, it sort of also generalizes in a slightly weird way, where you could sort of look at it as if it were sort of how closely identical two wave functions are, right? If a wave function is orthogonal to another wave function, these two wave functions are as different from one another as they can possibly be. So what is happening in this case where, you know, our tau expression, we found it to equal where was it? Yeah, we found our tau expression to equal something with a recurrence of n, right? Where for every value of n, it becomes orthogonal again. What's happening is that the wave function will sort of become in and out of phase with its x comma 0 initial state over and over, almost like sinusoidally, right? So this tau, by defining delta t in terms of tau, what you're really measuring is the amount of time it takes for a state to change to a point of unrecognizability, right? Because that's what orthogonality ultimately is. If two wave states are orthogonal, they are, once again, as different from each other as they could possibly be. So when you are measuring delta t with respect to delta e in this uncertainty principle thing, right, delta t and delta e are sort of related in that they sort of determine how fast a state changes from one phase to another phase. So if delta t and delta e both have to be multiplied to be greater than or equal to h bar over 2, this sort of sets a speed limit to how fast your system can change, and it's related to sort of the energy uncertainty of the system. To get a more intuitive sort of idea behind that, think of it as like, if your energy is spiked about some delta, right? If this is a graph of energy, right? If the energy is determinate, then the wave function isn't going to change, right? If energy is determinate, then this thing is going to 0. So let me write this in red. If energy is determinate, then delta E, which is the uncertainty in energy, goes to 0. In order to maintain that this product has to be greater than or equal to h bar over 2, the time for the system to change significantly based on tau goes up to infinity as delta E goes to 0, right? So that means that the more determined an energy state is, the more stable the energy of a system is, the longer it's going to take to change significantly, because if it has a definite stable energy, it's not going to want to change to some other energy state characterized by some other energy, right? Similarly, if you have a state that has, two spikes about E1 and E2, what this means is that, the wave function wants to be both at the state of having E1 and also the state of having E2. There's indeterminacy here. The state or the wave function is going to change its state over time to be in either E1 or E2 or some combination of both. In this case, as your undeterminacy or as your uncertainty in energy goes up, the more likely the state is to want to change. So the time it takes for the state to change is going to go down, respectively, to maintain this requirement of it being greater than or equal to h bar over 2, or to be exactly equal to h bar over 2, I suppose. Because in this case, we found that if you are defining the uncertainty in time with respect to tau, which is the time it takes for the system to change completely, you are going to get something that exactly approaches h bar over 2. And that's about it. Or that's sort of really all I wanted to get to, which is that this problem ultimately is trying to get you to understand what delta t even is in terms of, the Heisenberg uncertainty principle, right? In the same way that position and momentum are sort of our traditional ways of looking at a system, another valid way of looking at the system is looking at how the wave function changes, or how long it takes to change with respect to like the energy differential in the system.